So we can start.
Yep, let's start.
Let's start. Our speaker today is Andreas Rauh. I think that everybody knows him. So Andreas, the presentation of Andreas is about finite memory approach applied to verified pseudo-state estimation of fractional models for lithium-ion batteries. Just a very short introduction of our speaker. Andreas received his diploma degree in electrical engineering and information technology from Munich in Germany in 2001. His PhD degree from the University of Ulm, also in Germany, in 2008. And finally, his habilitation from the University of Rostock in 2017. After a research stay at Insta Bretagne in France with Luc, Andreas was appointed as a full professor at the University of Oldenburg in Germany, where he is the head of the group Distributed Control in Interconnected Systems since October 2021. His research interests include modeling, control, parameter and state estimation in the context of in the stochastic and in the deterministic frameworks. So Andreas, if you are ready, you can start your talk.
Okay, many thanks, Tarek, for your introduction, and it's also my pleasure to welcome all of you to today's presentation. And yes, as Tarek already has mentioned, we'll discuss two aspects here. First of all, yes, a novel procedure for finite memory representation of the pseudostate estimation of fractional system models. Yes, and on the other hand, this will also be directly applied to a simplified model of lithium-ion batteries. And in fact, that's an extended version of a conference, a paper that I've co-authored together with Marit Lahme. And yes, we'll present this work in July at the 12th IFAC conference on fractional differentiation and its applications in Bordeaux. Now, let's have a brief look at the contents of today's talk. And in fact, what I would like to start with is a brief motivation on how and why to use fractional equivalent circuit models, first of all, for modeling batteries. Yes, and then afterwards, we'll discuss the shortcomings of classical discretization approaches, for example, the Grünwald-Letnikov discretization scheme, and how to overcome those issues when we're aiming at online or real-time capable estimation yes, for such type of dynamic systems, which can then be readily implemented, for example, in battery management systems. Yeah, and one of the key ingredients will be to quantify the effect of truncating the series expansion that is related to the Grünwald-Letnikov discretization scheme. And this will be embedded into an integrator resetting techniques, which we especially develop here in this presentation for cooperative dynamic systems. And as already mentioned in the introduction of this talk, I will apply the procedure to a fractional order battery model before coming to conclusions. Now, how would people typically model the dynamics of battery systems? Yes, and one of the procedures that can be applied is impedance spectroscopy. And impedance spectroscopy is a technique where a battery is being charged and discharged with the help of harmonic currents. And the things that are being measured here are the terminal voltages. And if we would have a linear system model that, yes, is represented quite well, as for example can be seen here in the lower left corner of the slide, by means of an equivalent circuit in which a series resistance is included in order to represent instantaneous voltage drops that arise when changing the terminal current in a Heaviside manner function, or that also take into account delay phenomena due to the transport of charge carriers with the help of RC subnetworks. One would expect to see amplitude variations of plus minus 20 decibel per frequency decade when performing this impedance spectroscopy. And at the same time, you would also expect to see phase variations that correspond to integer multiples of plus minus 90 degrees or plus minus pi half in the frequency domain. Now, what you see in reality is something like the picture on the lower right side. You see magnitude variations that are not multiples of those plus minus 20 decibel per frequency decade. And you could also show exactly the same, for example, for displaying the phase responses. Now, the problem is how to represent such types of systems. On the one hand, what is obvious is that the equivalent circuit parameters are typically functions of the state of charge. That means the state of charge dependency should be modeled. And this is something that can be done by means of classical parameter identification schemes. However, the thing that is very hard to model with classical integer order system representations is the variation of the amplitude and also the phase, which contradicts those two aspects that are being mentioned here in the very first and second bullet point of the slide. And to obtain a low order system model that doesn't take into account too many parameters to be identified, what someone could do is to generalize this equivalent circuit model to a representation that takes into account transfer functions in which we do no longer have integer order powers of the Laplace variables, but in which we have some non-integer values, for example, typically from the range between 0 and 1. Yes, and this generalization could then be used in order to perform a mapping of the frequency response by means of those generalized transfer functions or frequency response characteristics that you can see on the slide. And from an equivalent circuit point of view, this would mean that we're replacing the capacitances and maybe also inductances that are present for very high frequent excitation currents in the system model by generalized system models with a constant phase, a constant either positive or negative phase. And those constant phase elements can be represented with the help of powers of j omega, where j is the imaginary unit, omega the frequency given here in radian per second, and the corresponding powers would then be multiples of fractional order power and power nu within the open interval from 0 to 1. Yeah, and these types of system models can not only be represented in the frequency domain, but especially when we want to perform state estimation or pseudo-state estimation, we're representing those system models in an equivalent time domain representation. Now, I think firstly, the question is, why did I say pseudo-state estimation and not state estimation? Is the important aspect here for fractional system models is that the time responses that we can either measure or that we have to simulate when numerically evaluating such fractional differential equations do not only depend the initial state at a single point in time, which would be the case for a classical integer order model, but they depend on the entire past of the system evolution. Yes, and this problem has to be overcome by means of suitable numerical integration schemes, which take into account those memory effects in a suitable manner. One option to perform a numerical evaluation would be a generalization of a classical numerical solution procedure, which you would know from the integer case, as for example, the explicit Euler method. And for the fractional case, this would be the Grünwald-Letnikov discretization scheme, which takes into account in terms of the sum here on the right-hand side in the formula, previous state or pseudo-state values coming from the past, and not only the initialization condition at the point of time tk. Now, what you already can notice here in this equation is taking into account an infinitely long past. That means really evaluating the sum from a finite starting index until infinity. That's something you can never do in practice. That means what people are typically doing is they're truncating the evaluation of the series expansion after some number of predefined terms, and they're typically neglecting the errors that occur when truncating this expansion. Now, what we have already done in a previous work together with Rashid Malti is to quantify the effect of truncating the series expansion with the help of an interval solution procedure. And the general idea for this quantification of the truncation errors was based on a publication of Igor Podlubny, which he had demonstrated in his book, where the shift of the initialization point in time of a fractional derivative from one point till some other point in the future can be quantified in a rigorous manner with the help of strictly determined interval. Now, what you have to keep in mind is those coefficients Ci that are included in this formula, they can be expressed in a closed form manner with the help of a generalization of the factorials of integer values to fractional then being given with the help of this gamma function that is depicted here on this slide. Now, the other reason why we want to limit the number of terms that are being included in the series expansion is also due to the fact that, for example, when we're considering battery systems, we want to perform pseudostate estimation at runtime. Yes, and performing pseudostate estimation at runtime definitely imposes a real-time requirement. And the real-time requirement means that we should know a priori how many arithmetic operations we want to execute in a certain time frame. Yes, and for that reason, the number of summons here in this discretization schemes should be limited a priori. Yes, and this is what is marked here in this as the red warning comment. In theory, we need to know the entire past of the system initialization. That means all pseudostates, they are complete evolution, yes, from the birth of the universe until the point t equals 0, when 0 is the point at which we are initializing the numerical evaluation. Now, there exist specialized definitions of fractional differential equations in the literature, and one of them is the Caputo definition. Yes, and in this case, it is assumed that the initialization for the entire past is given by a constant. Yes, and throughout the following slides, this constant here is denoted by x tilde. Now, let's go back 2 slides. What we then would see is for indices that are negative here in the sum on the right-hand side, we would have to take into account this constant initialization for the entire past. Okay, the nice thing is the coefficients here that are being included in this term is they're decreasing. They're decreasing with respect to the temporal past window that is being considered. But it's hard to quantify which number of terms are really necessary and after which number of summons you can fully neglect the influence of the past. Yes, for that reason, we're firstly performing a change of coordinates, a change of coordinates that allows us to get rid of this initialization for a very specific initialization function, namely for the very specific initialization of an x tilde here in the slide that is fully equal to a constant. Yes, and what you can see is that's just a linear transformation of the set of coordinates. We're subtracting from the true pseudostate trajectory x of t, the constant initialization, and in the sense of Caputo, the time derivative, the fractional time derivative of this constant is then equal to 0. For that reason, we can express the original differential equation model with the one given here in the third line. And what you see on the right-hand side at the moment, that's just a linear change of variables in which we're replacing x by the sum of z of t plus the constant initialization. And let's keep in mind that after this change of coordinates, we have a constant initialization set of t equals 0 for the entire past, and the initialization for the sake of compactness also of the following notations is being set here to t0 as the initial point in time. Now, what this allows us to do is, with this information, we can evaluate the Grünwald-Letnikov approximation, this discretization scheme that you have seen before, with finitely many summons. Now, when we want to reset at some future point in time, at a point of time t0 plus capital T, the initialization, again to a constant, what can then be done is we can modify the set of differential equations by firstly changing the initial condition, setting again the initial condition to an initialization that is entirely constant over the past, with an additive error bound here described by the variable mu. And this vector is defined in a component-wise manner, as you can see in the third line, by the supremum of the absolute value of the pseudostate evolutions from the previous initial point in time till the actual point in time after shifting the initialization from T0 till T0 plus capital T. Yeah, that's something that can be found in Podlobny's book, which is also cited here. And yes, that's a result that is known for at least 25 years. Now, what I would like to propose now is to use this new initialization, again with this entire path being equal to a constant, and the modification of the set of our FDEs with the help of those interval bounds. Those are symmetric between minus mu and plus mu here on the right-hand side. We would like to use this procedure in order to implement a set-based state estimation approach. Yes, and this pseudo-state estimation procedure, as for any other interval observer design, is simplified by a huge extent if our system models satisfy specific monotonicity properties. And those are monotonicity properties with respect to the initial conditions. Yes, and for those of you who have already attended a certain number of the previous presentations in the seminar series, you would have definitely seen the sufficient condition here that is shown here in the upper half of the slide. Namely, you could check cooperativity of a dynamic system model, a continuous time dynamic system model, by verifying that the partial derivatives of the state equations with respect to the states, and in this case, only the reachable states of interest outside the diagonal of the Jacobian are non-positive. Yes, and that's a property you would either say the linearized system model would obey a Metzler structure. That means it's a Metzler matrix here for a continuous time system model. Or in other words, what you could do is you could decouple the calculation of bounding trajectories, lower bounding trajectories V and upper bounding trajectories W for the entire time frame. Now, what is specific for the case of FDEs is we need an initialization also of the bounding trajectories for the entire path. That means for t less or equal the initial point in time t0, we are assuming that there exists an initialization with lower and upper bounding trajectories. And starting with those lower and upper bounding trajectories, we can evaluate then, according to the following slide, the bounding trajectories independently for the lower and upper bounds. Is then the prerequisite to separate both bounding trajectories is especially not only the Metzler structure of the Jacobian that I mentioned just a couple of seconds ago, but it's also necessary that in this case, the lower bounds of our state evolution remain non-negative. Otherwise, there may be some coupling terms between the lower and upper bounds. Yes, and what we can do is those assumptions, and those are easily being satisfied with the help of the suitable interval observer design. We can again use the integrator resetting procedure that we have seen before, but now in a slightly modified manner. We are resetting both the numerical evaluation of the lower and upper bounding trajectories at some point in time t0 plus capital T. And for both of those bounding trajectories, that means for the lower bounding trajectory V and for the upper bounding trajectory W, we're getting the respective truncation error bounds, which are then denoted by mu, either with the index V or W at the point or after the resetting length capital T. Now, when applying this resetting procedure for both of the lower and upper bounds, what you see in order to obtain conservative enclosures of the state trajectories, we can perform point-valued or crisp evaluations of the lower and upper bounding trajectories in such a way that the lower bounding trajectory is characterized by the lower state bounds ZV, the upper bounding trajectory is characterized by ZW, and for the lower bounding trajectory, we have to subtract the corresponding error bound previously calculated for the integrator resetting scheme, and for the upper bound, we have to add the corresponding error bound. Now, what is important for us is, especially when dealing with modeling of our battery system, the set of differential equations, and those could either be integer order differential equations, as I mentioned at the very first slides of today's presentation, or also those fractional system models. Those are being characterized by the fact that we have uncertainty in the dynamics matrix A of the unobserved system model. That means there exists some lower and upper bounds. A underlined and A overlined are the respective component-wise defined uncertainties given in terms of interval variables for each element of the dynamics matrix. The same also holds for the input matrix, for an input matrix B, again with component-wise defined lower and upper bounds. And typically we have also uncertainty in the corresponding output matrix. Now what we want to do is we want to design for our fractional system model a Lüneberger-like observer for this uncertain dynamic system model. And that means we're introducing a new dynamics matrix, a dynamics matrix AO for the observer, which consists of the original system matrix minus HC, where H is the observer gain matrix that is being used to feed back the deviation between the measured output YM, and its corresponding estimate that stems from evaluation of our measurement model, which in this case is linear but uncertain and comprises the output equation C times X. And for the numerical evaluation of the estimate, this would then be C times X hat. Yes, and furthermore, we assume that there exist bounded errors, bounded additive measurement errors, which are included here in this vector with a bold-faced Greek epsilon here, again with component-wise defined lower and upper bounds. Now the requirement for the choice of the observer gain is twofold. Firstly, we should make sure that the aerodynamics of our system are stable. And on the other hand, we should make sure that we can still apply our decoupling procedure for the evaluation of the lower and upper bounding trajectories. That means if the open loop dynamics of the battery system already obey the property of cooperativity, we should choose an observer gain matrix H that doesn't destroy the cooperativity properties. Yes, and finally, one could also optimize this matrix, for example, by means of H-infinity optimization procedures in order to desensitize the state estimates with respect to unknown phenomena, for example, with respect to process noise acting on the system dynamics. Now, under those assumptions, under the linearity assumption and taking into account the effect of uncertainty in the matrices A, B, and C, which propagate onto this observed system matrix AO, which I remind you is the difference of the open loop matrix minus HC. We can define the lower and upper bounding trajectories, yes, by determining component-wise the infima and the suprema of those expressions here on the right-hand side. And what you see is, firstly, we have an influence here of the lower bounding trajectory from the elements on the diagonal of the matrix AO, is those elements are being extracted with the help of an element-wise matrix product of an identity matrix with this interval matrix AO. That means this circle symbol here denotes the element-wise Adamar product. I is the identity matrix. Capital E is an only once matrix. And with this expression E minus I, we're filtering out the elements off from the diagonal. Yes, and there may be the case that the lower bound of the state trajectories or pseudo-state trajectories may change the sign. And in this case, this corresponding operator included here in the second line takes into account the reversion of the corresponding bounds that may then become necessary. Yes, and what you finally see here is in the third line, the influence of the control input may be characterized in such a way that depending on the sign of U, which in our case is the terminal current applied to the battery cell, may also change the sign. For that reason, we have an element-wise infimum to calculate the lower bounding trajectories and the element-wise supremum in order to calculate the respective upper bounding trajectories. Yeah, the measurement errors here and further uncertainty, about which we'll discuss in a few minutes, are included here in this interval vector epsilon here, this bald face epsilon, and the truncation error bounds are either subtracted or added according to the meaning of those equations, where firstly we have the lower and secondly the upper bounding trajectories. Now let's come to the modeling of the battery. And yes, for the sake of simplicity, we take into account a linear representation, a linear FDE equivalent circuit model, in which we have a state of charge-dependent open circuit voltage. We have a series resistant that is firstly assumed to be constant here. That's the resistance R0. We have this generalization of a first-order delay element with a constant phase element Q. And as the corresponding parameters for the system model have been identified in some previous research together with colleagues from the University of Applied Sciences at the Lake Constance, yes, in one of our previous publications where we performed a state estimation procedure using an online minimization that exploits a moving horizon estimator for the battery dynamics on the basis of an integer order model. Yes, and those measurements have then been used in order to initialize the parameters R0, R, and Q, as well as a polynomial approximation of the open circuit voltage. It's the corresponding state or pseudo-state vector elements are the state of charge, the voltage V here at this constant phase element Q, and the derivative of order 1/2 of the state of charge. Now, you may wonder why explicitly 1/2. Yes, this is a result also of the identification procedure. The result of the identification was that we obtained a derivative order that suits the actual measured values with very good accuracy if you have a derivative order that is extremely close to 0.5. And for that reason, to simplify the following procedure, we have set this value to this constant. As all remaining other uncertainties could then be added into a bounded additive error term here on the right-hand side to this fractional differential equation. Now what we see is we have system matrices A and B. Uncertainty could be included in the resistances here in the system model, in the resistance here being placed parallel to this constant phase element Q. We could have uncertainty in the variable Q itself, and finally also uncertainty in the parameters of the terminal voltage characteristic. Yes, and how this terminal voltage characteristic is calculated, I think is quite obvious. It's based on Kirchhoff's voltage law. We have to subtract from the open circuit voltage the voltage drops here at the constant phase element and also the voltage drop here at the series resistance R0 in order to get the measurable terminal voltage V. Yes, and this terminal voltage is then available as a measured output for our estimator. And we assume voltage measurements with a tolerance of plus minus 10 millivolts here at each point in time. Now what you see, let's go back to the slide again. We have nonlinear expressions here included. Those nonlinear expressions are firstly polynomial terms in the state of charge. That means the kth order power here of the SOC being included in the output model. As this results from the identification of the voltage state of charge relationship of the open circuit voltage of our battery. And there's also one exponential term here included. Okay, the exponential term doesn't play the major influence if we're operating the battery cell at some reasonable values of state of charge. But what is obvious is that this nonlinear phenomenon here, with those powers of the state of charge itself, they play a major role. Yes, and they also contradict the property of a pseudo or quasi-linear system representation for the observabilities. Yes, for that reason, we made a small modification of the output equation, and we're subtracting from the actual measured system output an evaluation of this nonlinear term at the interval midpoint of the current state of charge estimate. Yes, and all remaining deviations are then being shifted into an interval term here, into this term v tilde minus v tilde evaluated at the midpoint. And yes, in the case that we're setting the parameter gamma equal to 1, this includes with 100% certainty all possible linearization errors. And if we're choosing a value between 0 and 1, we could check then the sensitivity of the state estimation procedure with respect to additive error bounds. Now, what you can also see here, this is definitely not the only way how to linearize this output equation. And one option to linearize the output equation would be, for example, also to use a centered form representation. But since we wanted to focus here in this presentation really on the scheme for integrator resetting and not on the most sophisticated procedure for linearizing in a set-based sense, the output formula, we're just using this naive representation, which is definitely more conservative than necessary. Now let's come to some simulation results. What we have investigated is for different uncertainty levels, 0 till 1, as here gridded with the values 0, 0.25, and so on, a constant discretization step size of 100 milliseconds, and a 5% uncertainty in the initial state of charge, where the actual state of charge was 80% here on the left-hand side. We're evaluating firstly the numerical simulation with the help of the Grünwald-Letnikov scheme by exploiting the property of cooperativity of our system model. The system model was, in this case, the observed state space representation that you had seen here just a couple of slides ago. Now, what we can notice firstly is for quite small values of gamma, we always get, and that's also something you can see in the enlarged view here on the right-hand side, a guaranteed enclosure here that is contracting and including the true evolution of the state of charge, which is given here by the dashed line. For larger uncertainty of gamma, what can happen is that our system dynamics become unstable. And now we have to go back a couple of slides. This unstable behavior is caused by the fact that our output matrix C, in this case, is evaluated at runtime for the estimate of the state of charge. And now what could happen is if we have a very pessimistic estimate of the state of charge, a nominal stabilization of the aerodynamics doesn't guarantee asymptotic stability of the behavior in the case that we have an inflation of the interval diameters being included in the uncertainty of C. Okay, there's a very simple way how to resolve that issue. The simple way how to resolve that issue, and that's also a subject not of today's presentation, but also for future work, would be to reduce the pessimism with the help of a contractor-based approach, a contractor-based approach that has been presented last year at a conference in Poland at the MMIR conference by my co-author Marit Laume. And that's a procedure that could be used in order to eliminate from the evaluation of this output matrix C intervals or subintervals which are inconsistent with the original polynomial formulation. Now having a look at the other pseudostate variables, those are on the one hand the derivative of order 0.5 of the SOC. That means here in this case, we always have a very accurate tracking. And yes, the blow up of the bounds in the case of a large uncertainty is not only visible, as we had seen on the previous slide for the SOC, but it is also visible here for the voltage at the constant phase element. Now, the interesting thing will be, are we able to reproduce this behavior with the help of our integrator resetting procedure? Now, the idea of integrator resetting is to limit the number of summons in the evaluation of our right-hand side, or of the right-hand side of the Grünwald-Letnikov discretization scheme. Now, what we would have here is, if we do not apply this integrator resetting at each evaluation point, a further summand comes into play, and that means over time continuously growing computational complexities for the evaluation of those bounds of both the lower and upper bounding trajectory. To prevent this, we have included here the resetting scheme, a resetting scheme after each multiple of 1,200 seconds. That means after 20 minutes. In our case, that's a resetting here after 12,000 evaluation points with a constant sampling step size of 100 milliseconds. And what you see is practically very close behavior to the thing that we had on the previous slide. But only at those points in time where we're resetting, we get an additional influence of uncertainty. And this additional influence of the uncertainty then leads to widening at the points of integrator resets, the corresponding enclosures of the pseudostate evolutions. Yes, and this is further also propagated to the 1/2 derivative of the SOC and also to the voltage at the constant phase element. Now, if you would look at the conference paper that I've mentioned at the very first slide of today's presentation, you further see one small drawback. And the small drawback can also be seen here in the evaluation of the bounds for the 1/2 derivative of the SOC. Yes, and the thing there is, this eigenvalue with the help of the observer approach unfortunately can only be made marginally stable. That means there's a remaining fractional order integrator in the system model, which leads to a continuous blow up of the bounds. And yes, one option how to circumvent this would then be to use a set-based estimator that takes into account not only the single degree of freedom, namely the observability matrix or the observer matrix itself, but which takes also into account further degrees of freedom, for example, by means of a quite well-known TNL observer structure. Yes, and this already comes me to the conclusions of today's presentation. What you have seen today is the option of a novel finite memory approach for the numerical evaluation of fractional differential equation models, which is especially based on quantifying the effect of truncation errors in the case that we're resetting fractional integrators in such a way that we're defining new initial points in time before which we have fully constant initialization functions in the sense of Caputo. The influence of this constant path then was eliminated with the help of a linear shift of coordinates to eliminate those constant initialization functions. And finally, we have applied this estimation scheme to implement pseudo state estimation procedures, which are set-based. That means generalizations of interval observers, including an integrator reset with a finite memory property, which has then been applied to battery models. Yes, and the future work definitely takes into considerations one of those or two of those aspects that I've just mentioned before. Firstly, we should refine the time domain truncation errors with the help of a suitable observer approach. As fundamentals for this have been laid 2 years ago in a joint publication with Rashid Malti. The second thing is we would like to enhance the pseudostate estimates, especially for quasi-linear system models, by eliminating physically inconsistent parts of this conservative enclosure of the system matrices A, B, and C. For that purpose, we can exploit a contractor-based procedure. And lastly, what would be of interest is to refine the knowledge about the initialization functions. And as from our perspective, we assume that one of the promising procedures could be an observability matrix-based interval estimator, which, for example, has been recently also been presented in the seminar series here by Nassim Mislem and Nassim Ramdan. And from that point of view, there's a list of related publications. I'll put also the slides on the ResearchGate profile that you can have a look at those publications. Especially the third one here from the list will be the corresponding conference paper, which will soon appear after the conference at the beginning of July. Yes, after it has been held in Bordeaux. Yes, and the others are related publications from my research team. And yeah, without any further words, thanks a lot for your attention.
Thank you, Andreas, for this very interesting presentation. I think that we have time for some questions. Who wants to start? Yes, Luc.
Yes, thank you, Andreas, for the presentation. I would like to ask you a question about the Grünwald-Letnikov discretization. So it seems that it works, it is an exact discretization, yes, and it works even if the system is non-linear, non-cooperative, and things like this, yes? It is general?
Yes, this discretization is general, but please be careful with the word exact. We have a finitely large discretization step size. That means what has been neglected here is the effect of temporal discretization.
Okay.
Yes, and that means what we did here is, let's come back to the example. The example is we had identified the time constants here. That means the reciprocal of the real part of the eigenvalue of our dynamics model. And the discretization step size has been chosen at least by a factor of 10 smaller than the corresponding most critical time constant, in order to avoid problems like you definitely know from applying any other discretization scheme also for integer order models like the Euler method, Rauh method, or something else.
Yeah. Yes, because in the example you have shown, most of them are are linear or cooperative, and it is you think that the approach could be generalized to the case where it is not cooperative and non-linear?
Yes and no. Okay, firstly, for nonlinear cooperative, this works very well. Because then what you could do is you could embed the nonlinear dynamics into the uncertainty in the matrices A, B, and C. And that's also something we quite often have already done in the integer order case. And I do not expect any problem there. For non-cooperative problems, the problem is how to evaluate, how to propagate the interval bounds. Yes, and propagating the interval bounds directly with the Grünwald-Letnikov scheme would then become difficult, because then what you get is a wrapping effect in the evaluation of this formula. And that means you have two options how to fight this. One option would be use, for example, sonotopic enclosures. This would be an idea. If you have sufficiently strong stability properties or contraction properties, this could work. The other idea then, what I would suggest is to use something like, a function prototype that is enclosing the true evolution, for example, Mittag-Leffler function or exponential functions. And on basis of this, one could generalize a Picard iteration scheme in order to enclose the dynamics. And I think this would then be more efficient if you have a really nonlinear system model for which you can show stability, but which you cannot transform into a cooperative representation.
Okay, thank you. And probably if I have time for a last question, yes, if possible.
Yeah.
I would like to, so you at the beginning you show a state equation where the derivative is new times, if you want, yes, this one, and I would like to know how in the case where nu equal to 1, so you obtain a classical state equation, okay? Then probably all the procedure, so when nu equal to 1, of course, classically we use a Picard operator because we know that the solution is unique. And if your approach would be used, for instance, in the case where nu equal to 1, do you think to what kind of method it would correspond?
That's extremely simple. This Grünwald-Letnikov scheme is then the explicit Euler method. That means all the coefficients Ci that you see there in this summand on the right-hand side become 0.
Yes.
And the truncation errors also become 0.
Yes. So
that means it's really a temporarily discretized version of this system model with the help of an explicit Euler method. And as I mentioned, as a reply to your first question, what we neglected here is the temporal discretization error.
Okay.
This would still persist then, and that's a conversion of the continuous time ordinary differential equation then with the help of an explicit Euler scheme with sufficiently small delta t.
Okay. Thank you. Thank you.
Thank you, Luc. Thank you very much. Are there some other questions from the audience, please? I have some small questions, Andreas. The first one is about slide 3. What about the Bode diagram? Is it obtained by real data or in simulations?
This thing here was copied from a publication.
Yeah.
And this was really obtained from real data. What you see is those different colored lines. They are obtained for significantly different temperatures.
For a battery?
Yes, this was a battery, a lithium-ion battery, operated at totally different temperatures, ranging from around -20 degrees till +50.
Okay, thank you. Could you please put slide 8? What is the variable x tilde? Is it the initial state? It's not clear for me for the change of coordinate.
We have to go one slide back. It's this one here.
Yeah.
It's the assumption that we have this autonomous FDE with an initialization that has x tilde as the initialization from -infinity to t index 0. But that means the entire past was initialized with a constant.
Is it a noun or a noun constant?
It is typically unknown.
Yeah.
But for the interval observer design, it would be a conservative over-approximation.
Okay. And how to obtain the change of coordinates in practice for a given system?
Intelligent guessing.
The same slide, slide 8, please.
Yeah, no, this is intelligent guessing. What you would do in practice is you assume that your system model was sufficiently long at rest, your battery, for example. Yes, and then you can estimate the worst case lower and upper bounds of the previous states. Yes, and this is how you obtain x tilde. You're guessing the upper bound, you're guessing the lower bound, and then you have two changes of coordinates, one for the upper bounding system, one for the lower bounding system. For each of them, you're forcing the history to 0 by subtracting this initialization condition. And then you know between those two bounding trajectories, the actual evolution of the system dynamics will be. But again, under the assumption that I made a good guess for x tilde.
Okay.
Yes, and at the moment, this is pessimistic.
Okay.
In the future, work will be really to identify x tilde.
What about the uncertainties? I think that slide 18. What about the uncertainties, constant or time varying uncertainties in the state equation, in the matrix A? What about the assumption for the uncertainty?
In this evaluation, there can be time varying. And in fact, there are time varying in the matrix C at the moment. We have this output matrix, which depends on the current estimate of the state of charge. And that means we have a new output matrix at each point in time. And that means we're updating the matrices in the Grünwald-Letnikov scheme also after each estimation step.
My question was about the matrix A. You have the last term, RQ, the inverse of RQ. Is it a constant or time varying term?
If you're operating the battery at constant temperature, you could place it to a constant.
Okay.
If you have significant temperature variations, then definitely it's temperature dependent. This must be identified. The same would also be the Q and this eta 0 in the matrix B.
Yeah.
And what is also happening in reality is degradation. Yes, and due to aging, what you could have also slow variations of R, Q, and eta.
Okay, so since the matrix C is an uncertain matrix with some time varying parameters, how to ensure the stability of the estimator? Because we have the matrix A minus HC or something like that.
Yes.
What is the technique which is used to ensure the stability?
At the moment, it's really just you assume a priori some bounds for C.
Yeah.
And yes, then what you have is you can write down a polytopic uncertainty model.
Okay.
Yes, and with a polytopic uncertainty model, you would be do something like pole domain assignment.
Okay. And
And
are you
for
able
for the fractional model, you have this sector opening into the right half plane of the complex S domain. Yes, and then you just have to choose a domain of eigenvalues that is compatible with this sector.
I have a last question. Are you able to introduce some performances and indexes such as peak-to-peak or H-infinity or something like that? For, in addition to the stability, some information about the performance, the
problem is here for this model, we are already quite restricted with respect to the choice of the elements in the observer gain matrix H. Yes, and this restriction comes from the fact that we do not want to destroy the Metzler structure, this cooperativity property. Yes,
yeah,
and for that reason, it's very hard to impose further optimality criteria in this formulation. You have very bounded degrees of freedom. What I would then just do is generalize the observer after the discretization to a TNL procedure, and then you have the sufficient degrees of freedom that we need.
Yeah, because for known fractional systems, there are some results about the performances. We can ensure the Metzler properties, so the positivity, but also some performance. There are some results for known fractional systems. I don't know if you can extend these results to fractional systems.
Yeah, is that the problem is if you look at the output equation, you see fundamentally the matrix C in the first term. That means we have an element. The first one is positive. It's quite ugly, the analytic expression. The third one is strictly negative. It's constant to -1. Yes, and this makes it difficult. That means you really have a bounded domain in which you can only preserve the Metzler property.
Okay.
And that means, for example, the last element of the observer gain matrix must always be negative. Yes, and in other cases, you would immediately destroy this property because this would then influence here in the upper right corner of the matrix A, this element, the 0 element, and this would then be turned to a negative value otherwise. And that means in such cases, if you need this as a degree of freedom to play around with the last element of the observer gain matrix, I would suggest generalize the TNL procedure.
Okay. Thank you, Andreas.
Yes, but maybe that's something we can do together.
Okay, it will be my pleasure. Are there other questions, please, in the audience? I think no. So thank you very much, Andreas, for this very interesting presentation. Thank you.
Also from my side, many thanks, Tarek. And also many thanks to all participants, and definitely we'll continue our seminar series, but I think most likely the next presentation will be in 4 weeks.
Okay.
Okay, see you soon.
Thank you. Bye-bye.
Thank you, bye.
Bye.